Sir, I think we can start, so let others join in the meantime.
Okay. Yeah.
Arasu, sir?
Yeah.
Arasu, sir? Arasu, sir?
So we'll start.
Yes,
Good
sir,
afternoon.
we can start.
On behalf of the Institute of Indian Foundrymen, Coimbatore chapter and NCDST, National HO, jointly organized a technical webinar on demystifying the iron carbon diagram, a phase transformation perspective, by guest speaker Mr. P N Raghavendra, founder Raghavendra Metallurgical Solution. Now request IAF Coimbatore chapter chairman Mr. V. Sivaprakash sir, warmly welcome the gathering.
Good afternoon, everyone. I hear now.
Yes, sir. Yes, sir.
Yeah. Good afternoon, everyone. It gives me great pleasure to welcome you all on behalf of the Institute of Indian Foundrymen, NCST, and Coimbatore chapter jointly organizing the webinar. We are delighted to have you with us for today's technical webinar on demystifying the iron carbon diagram, FS transformation perspective. This is fundamental topic in metallurgy that plays a vital role in understanding the behavior of iron and steel during heating and cooling. A clear understanding of phase transformations helps foundry professionals improve casting quality, process control, and material performance. Today's webinar is an excellent opportunity for engineers, metallurgists, students, and foundry professionals to strengthen their technical knowledge and gain practical insights from an experienced expert. We are privileged to have with us our distinguished guest speaker, Mr. Raghavendra B N, founder of Raghavendra Metallurgy Solution. Sir has extensive experience in metallurgy and has been actively guiding industries through his technical expertise and practical approach. We sincerely thank him for taking the time to share his valuable knowledge with us today. I also extend my heartfelt thanks to all of the participants who have joined in this webinar from different locations. Your enthusiasm for continuous learning and professional development is what makes programs like this meaningful and successful. I encourage everyone to actively participate, listen carefully, and make the best use of this interactive session. I am sure today's webinar will provide valuable takeaways that you can apply in your professional work. Once again, a warm welcome to our respected speaker and each one of you. I wish you all very informative and engaging technical session. Thank you and have a great webinar.
So thank you, sir. I'm very privileged to introduce today guest speaker, Mr. P N Raghavendra, founder Raghavendra Metallurgical Solution. He's basically complete diploma in metallurgy engineering. Subsequently, he completed Bachelor of Metallurgical Engineering and MS in Total Quality Management, Certified Six Sigma Black Belt Trainer, Learning 3.0 Management Program Special Design for Mahindra participants. A multi-facet metallurgical quality professional with more than 20 years of rich experience in managing the operations involved in quality area of automobile industries. He has professional in quality plans such as failure mode effect analysis, product analysis, APPAP, 7QC, and quality control charts. Professionals analyzing field of failures, various process, and identifying the gaps in the process. These are the experience in the various area. He's a certified lead auditor, statistical decision making, supplier quality management, QMS, innovational thinking. Is a significant highlighted is responsible for supplier quality management, supplier QMS audit, auditing and improving the special process of suppliers. He attended the many course and training in the area of Six Sigma, Six Thinking Hats, statistical decision making, Mahindra Yellow Belt, QMS lead auditor, welding technology, presentation skill, leadership development program, laboratory management internal audit, basics of paint and its applications, Young Engineer Excellence Program, Office of TPM and 5S, lean manufacturing, 7QC tool and QC story approach. It's a very vast experience in various areas of manufacturing industries. We are very fortunate to have such a eminent person as a today guest speaker. So on behalf of NCTS and IF County chapter, once again warmly welcome and privileged to introduce today's speaker, Mr. M. Raghavendra. Sir, now you can initiate your presentation.
Yeah. So thank you very much for Indian Institute of Foundry and all the dignitaries, and many senior people have joined. Okay, so this is a basic concept for metallurgists. I hope many of you are metallurgists, or many of you may be non-metallurgists. So let us start and learn about iron carbon diagram. We have learned in the college, so today we will make it more clear. Okay, and I will explain in a simple language, and I hope my web desktop is visible, right?
Yes, sir. Yes, sir. You can proceed,
Yeah.
sir.
Thank you. So basically, today we will learn about iron carbon diagram. That is actually a phase diagram. So before that, so just to start with, and some people are still joining. So we will just understand some basics. Okay, we have learned in the college school that every material is made up of atoms. Okay, I think some of you may be writing in a book. Okay, so if you think I want a thickness of a paper, I want to make a thickness of paper using the atoms. If I keep on adding the atoms one over the other, so minimum 5 lakh atoms is required. So that is that much small. Okay, and in Greek it means unable to cut. Okay, and we have studied the atomic structure. So this some basic portions I will go fast. So when we reach iron carbon diagram, we will discuss in detail. Okay, this is basic, and you know that these atoms bond together to create a solid crystalline structure in the metallic bonding. Okay, so in metallic bonding, these atoms bond to create a solid crystalline structure. Okay, so whatever the valence electrons we see here in the atomic structure, so in metallic bond, what happens is these valence electrons, actually these are we call it as a sea of electrons. So these are actually it is moving around, and still it will help in the atoms to create a bond. So that is why we know that all the metals are good conductors. Okay, so if you heat, the heat will pass from one side to other, and if you pass a current, it is electricity will pass. So that is because of the metallic bonding. These are made up of atoms. This will have a crystalline structure. What do you mean by crystalline structure? See, whenever we cool from the liquid state, in crystalline structure, as you are seeing in the picture, so it will arrange in a perfect crystal lattice structure. So it will have a perfect arrangement. So all metals and ceramics generally have a crystalline structure, and whereas glass, polymers, it will have a random structure. It will not be a arranged structure. Atoms will not be in order. So we know it as amorphous material. Okay. So metals and ceramics are crystalline structure. So if I want to write down these atomic arrangement in a 3-dimensional, okay. So generally we call this as a space lattice. Here what happens is every atom is having identical surroundings. It has identical surroundings, and this we call it as a space lattice. And in this space lattice, if I identify a smallest area that which repeats, it will form a space lattice that is known as unit cell. This we have learned. Okay, so this is the unit cell, and basically you know there are 7 basic crystal systems. Okay, simple cubic, tetragonal, orthorhombic, hexagonal, triclinic, monoclinic, rhombohedral. These are the crystal system. That means whenever the small atoms, what we discussed, when it is in the metal, it will arrange. So it will arrange in crystal systems. Okay, basically in general, we discuss about three crystalline structures, that is body centered cubic, face centered cubic and hexagonal closed pack. So what is body centered cubic, face centered cubic? See, if you see there is a one atom at the center. So this is actually a body centered cubic, we call it as, and all the corners will having a atoms. In face centered cubic, actually all faces will have a one atom and the other eight corners will have atoms, like that in hexagonal. So this is actually a unit cell of a body centered FCC and SCP looks like this. And just now we understood that it is having identical surroundings. That means if you talk about the next unit cell, so it is sharing its atoms. Okay. So when I take a unit cell in a three-dimensional view, it looks like this. So this is FCC and this is BCC and HCP. Here if you see, only the portion of the atom is with this unit cell and the other portions will be sharing with the other unit cells next to this. So there is some voids you are observing, okay, there is some gaps are there. So we can calculate how much volume of the atoms present in a particular unit cell. So this we call it as an atomic packing factor, okay, so volume of the atoms in the unit cell. So that is for FCC 74% and HCP also 74%. For body centered cubic it is 68%. So this is basic, just you all know this. I'm just to start with, I'm discussing these points. And just now we understood that whenever a metal cools down, so it will form a crystal structure. But the crystalline structure, whatever we have seen here, it is a perfect order, okay. But generally all metals will not have a perfectly orderly arrangement like this. It will have some defects, okay. So this you all know there are four types of defects. We call it as a point defect, line defect, planar defect and volume defect, okay. So these are the four types of defects. Point defects, generally it occurs at any point, okay, we will see it in detail. Line defect, surface defect and volume defect. See, it is actually an additional atom going in the smaller size. So this is at a particular point, that is why we call it as a point defect. Here actually one atom is missing, so this is also a defect. Here some bigger size atom is sitting. So since it is occurring at a particular point, we know it as a point defect. And if the small atoms go and sit inside the voids, we call it as a interstitial alloy. Okay, interstitial alloy, because see, if you compare iron and carbon is having a smaller atomic radius, it can go and sit in the void. So we call it as an interstitial alloy. Substitutional alloy means the same size or slightly bigger size will replace an atom. So we call it as a substitutional alloy. Here we need to understand one thing, even though it is a point defect, so we are going to use this defect for changing the mechanical properties of steel or cast iron, casting. How we can change? Like for example, you all know heat treatment. See, we do case carburizing. So when we do case carburizing, the carbon atoms, how it is going inside, that is through a diffusion process, it will go and sit in the voids present in the face centered cubic structure. So that this point defect, we are using it for the changing the mechanical properties. And line defect, actually it is known as also dislocation. So here the entire line of atom is missing. If you see in this, entire line of atoms is missing. So this is the origin of edge dislocation. So entire line of atom is missing. So we call it as a line defect. Okay. But depending on the area which you are seeing, so here the one line of atom is extra, here one line of atom is missing. So we call it as a positive dislocation and negative dislocation. So this is just basic. We'll touch the phase diagram. See here, the surface of planar defect, you all check daily the microstructure of any casting or steel you are checking. So that is basically a surface of planar defect. How this defect occurs? See here, Just now we discussed, say, about body-centered cubic. Consider that all these crystalline structure, whatever we are seeing, these are all body-centered cubic. But what has happened is, while cooling, if you see carefully, so the orientation of this and orientation of this, even though the crystal structure is same, orientation is different. Whenever there is a orientation difference, there is a gap occurs, and that area we call it as a grain boundary. So these are the grain boundaries, and these are the crystal structure. So because of this orientation, different orientation, it will have planar defect. And this planar defect also we are using to change the mechanical properties by changing the grain structure. Okay. So this is a grain boundary, and single individual area we call it as a grain. So as we discussed, point defect, line defect, if there is no line defect, we cannot give the deformation. Okay. So material will not move. So line defect is required. Point defect, you can use it for changing the mechanical properties. You can diffuse different metal inside depending on the size. And the planar defect or surface defect, this we are using it to change the mechanical properties, changing the grain size. Volume defect, actually it is not acceptable in any metal, like crack, inclusion, micro cracks or porosity. So this is not acceptable. Okay. For porosity, casting, if you are making, that is depends on the area, how much, and there will be some acceptance criteria. But generally, volume defects will reduce the strength of the metal, so that is not acceptable. In metallurgy, we should understand one term called solid solution. Generally, what happens? Solution means in our thinking, just we come to know that solution means something liquid. Okay, but in metallurgy, solid solution means, so there will be two elements. Let us say, for example, we discuss about first we discuss about regular solution, that is water, and you take a sugar or salt. Okay, when we add sugar to the water, so it will mix, so it has become one solution. Okay, likewise we can mix two or more elements in metallurgy and it will become a solid, so that is known as the solid solution. Here in the water sugar example, water is actually a solvent and sugar is a guest, we are adding it. So guest is called as the solute. Okay, host is a solvent. Likewise, for example, brass, we know it is a alloy of copper and zinc. We call it as a solid solution of copper and zinc. Now, by understanding this, you should understand solubility. This is the one more term, solubility. Like for example, whatever we discussed regarding water and sugar. And if I take a 50 ml of water and add the sugar, say one or two spoons, maybe it will dissolve. And if I keep on adding at particular time, a particular quantity of the sugar, it will not solve, it will not dissolve. So then we may have to heat it, and after heating also, again if you are keep adding without adding the water, there is a certain limit. After that, the solubility will not be happening. It is just a mixture. Like that, in the metals also, there is a certain quantity we can add, certain percentage, depending on the elements. So that is known as the solubility. In metallurgy, these solubility limits, how much we can add, how much it can take, so that we will understand through phase diagrams. So this solubility at different temperatures, what will be the phases, whether it is a liquid, solid, insolid, what is the crystal structure. So these all things we learn it phase diagrams. So this is a tool in metallurgy. We have learned iron carbon equilibrium phase diagram in college and school. Okay, so what is phase diagram? Basically, it is a graphical representation of different phases present in an alloy. Okay, at different conditions of temperature and chemical composition. I hope I'm not going fast. Is it okay? This much speed? Hello?
It seems to be okay, sir. Somewhat little
Yeah.
bit slower, sir.
Okay.
Maybe
So
some initial new
okay.
people's may.
Okay. So now let us understand what is iron carbon equilibrium phase diagram. See, equilibrium means here in metallurgy, in iron carbon equilibrium phase diagram, let us say equilibrium is very slow. Okay. So I am going very fast. So very slow, extremely slow process is known as equilibrium. Let us understand that. Say for example, if I want to heat the metal from say around 30 degrees to 31 degree, I want to increase the 1 degree of temperature. So I may take around 4 to 5 hours. Like that you can imagine. So that much slow process. Okay. So that is the equilibrium. Okay. So they have done investigations, and if you take pure iron, that is 100% iron, if you start heating from the room temperature, you go on slow heating. Okay. So at room temperature, so what we are seeing is it is the ferrite, that is structure is in BCC form. Okay. So I go on heating slowly, and when I reach 912 degree, above 912 degree, that is ferrite is converting into austenite. That means body centered cubic. It is in solid stage only. It is converting, it is changing the structure BCC to FCC. Okay. Then if I go on slowly heating and reach around 1394 degrees, what is happening is FCC is again converting into BCC. That is austenite is converting into ferrite. And if you go on still heating at 1538 degrees, what is happening is it is starting to become liquid. So we call it as a melting point. So pure iron, the melting point is 1538 degrees. Okay. And above this, it is completely liquid. Okay. So pure iron, very slow heating. What I am doing is very slow heating from the room temperature. So these are the different structures. Ferrite, it is converting to austenite at 912. Then at 1394, it is again converting into ferrite. But at 1538 degrees, it has become liquid. So this we have understood. Now, what I will do is, so like water and sugar example, what we took, what I will do is I will add 0.0001% carbon, and then I will observe the phases. Then I will add more carbon. When I am doing like that, so you can see here, this is actually the first, this line is a completely pure iron, whatever just we discussed. This is a pure iron line, this line is, okay. This 0 means it is 0% carbon, 1 means 1% carbon, 2 means 2% carbon. So that means horizontal line we are increasing the carbon percentage. So this is the temperature, and this particular 0, this line is 100% iron. So if you observe, what is happening is, if I go on adding the carbon, the melting point, so this is a completely liquid, right? The melting point is coming down. Okay. So below this area, it is liquid plus solid, and below this area, this is a completely solid area. Okay. Here what happens is, actually it is a 4.3%, it will immediately become solid. Okay. This area is solid. So here it is liquid plus solid. I hope you have got it. Now here actually that is not mentioned over here, 6.67. So 6.67% means 6.67% of the carbon we can add into iron. Okay. So above that, it is not a solid solution, it is just mixture. So with this phase diagram, so we will understand that we can add up to 6.67% carbon, and what are the different phases we will discuss in later. Now we will understand what is ferrite. See, ferrite actually it is Latin word taken from ferrum. It is a BCC structure, body centered cubical structure. Okay, we call it as alpha iron. Because we should know this to understand iron carbon diagram. There are different crystal structures like phases like ferrite, austenite, pearlite. This we are going to discuss. So ferrite is body centered cubic. Pearlite actually it consists of alternating layers of ferrite and cementite. Okay. So ferrite, just now we discussed ferrite and cementite. Cementite is actually having a orthorhombic structure. Okay. So you can just imagine there is a cabbage. You have dipped the cabbage in a water. So water is a ferrite, cabbage is a cementite. So whatever the gaps are there actually water will enter. So if you cut it, then you will see the alternating layer of the cabbage and water. So like that, the ferrite and cementite layer, we call it as a pearlitic structure. So cementite is the orthorhombic, we call it as Fe3C. It will have a 6.67 or 6.7% carbon. Austenite, it occurs at a higher temperature. It is face-centered cubic structure. Okay. So this is FCC, face-centered cubic structure. Now, for example, if I take a 0.4% carbon, see in iron carbon diagram, up to 2% we call it as a steel, and more than 2% up to 6.67% we call it as a cast iron. And if you take a 0.4% carbon steel, so here it is completely liquid, and now from this area to this area it is austenite plus liquid. Okay, how it will form we will see, and below this point it is completely solid, and up to this point it is completely austenitic structure, and below this again it is austenite plus ferrite, and below this it is ferrite plus pearlite. This is how the transformation takes place. That means we need to add 0.4% carbon into the iron, that is 0.4% carbon steel. When we go on heating, this is how the transformation takes place, and it is a reversible process. If you go on cooling also, the same phase transformation will take place. So we will see this through this video, you will understand. Actually it is a equilibrium, that means equilibrium is very, very slow, but this is just for understanding. You see here, so this is completely liquid, right? Now when it touches this point, this is liquid plus austenite. So this is how the crystal grains grow. Now it is completely solid. It is austenitic structure. So now what we are doing is we are slowly cooling it. So once this touches this temperature, so there is austenite plus ferrite transformation takes place, and this is a 723 line, that is a critical temperature line. So below this the transformation will be ferrite and pearlite. So basically if you see this is around 0.3% carbon we have seen. This is how the transformation takes place at a equilibrium. Equilibrium is very slow. And now if you want to heat it from the room temperature to the melting point, the same whatever we have seen, the same process will repeat. That means if we are slowly heating it, so the ferrite and pearlite at this temperature above 723, it will transform to austenite and ferrite, and when it crosses this, say about around 830, 840, so again it will convert to austenite. So here it will become austenite and liquid, then it is completely liquid. So this is how the phase transformation takes. So if you see for say for example 0.8% carbon, so it is completely liquid now. So this is liquid plus austenite. Now it has become completely austenite. So austenite is a FCC structure. So when it touches 723 and below that, since the carbon is more, it will completely transform to pearlitic structure. Perlite means it is the alternate layer of ferrite and cementite. So this is how the iron and carbon equilibrium phase diagram, actually the phase changing happens at different composition. Now if you see, this is a 6.67%, this is a maximum limit. So up to 2% we call it as steel and 2 to 6.67% cast iron. Now, for example, if I want to increase the cooling rate, we have understood equilibrium means slow cooling. So when I am doing a slow cooling, so this we have understood ferrite and perlite will form. But when I change the cooling rate, so around sudden cooling, when we do rapid quenching, we get martensitic structure if the carbon percentage is low, and otherwise moderate cooling we get a binary structure. So generally, if you see any iron carbon equilibrium diagram, you will not see binate or martensite given in the diagram, because see what is happening is we are for martensite, to achieve the martensite we have to do rapid quenching. So rapid quenching will not have equilibrium phase. So equilibrium means very slow. So when we do very slow cooling, we get
That's a question on no. Raghavendra sir.
percentage. So we will not get the
Raghavendra sir. Let us wait 1 or 2 minutes. He will join again. The trainer will join again. Let us wait 1 or 2 minutes. Yes, sir.
it got disconnected, no?
Yes, sir. You can proceed, sir. Load your.
See, basically, what I would like to understand from any one of you, say for example, I have a 4.3% carbon cast iron. I want to make it completely liquid. So by looking at the phase diagram, so can anyone tell, so what is the temperature we need to reach?
Thousand 147.
Yeah, see 1147, if you go above 1147, it is completely liquid. Say for example, you have a 0.8% carbon steel casting, and you want to achieve completely austenite. So what is the temperature? what is the ideal temperature which you can select to achieve completely austenite phase? Say for example 0.8% carbon steel is there.
1492.
0.8% carbon steel is there. See, that is why I am
723.
asking.
723.
Correct. So why I am asking these questions is basically from today onwards we need to understand how to read the phase diagram. So 0.8% carbon steel. So if I go on heating it, so you can see here. So the point E above this it is completely austenite. So this line is horizontal line is 723. So once you reach here, it will be completely austenite. Very good.
Okay.
And overall, in iron carbon diagram, at what percentage of carbon you can achieve the lowest melting point?
Overall. Around 1100.
See, what is the lowest melting point in the iron carbon diagram?
1147.
1147. 1147 is the lowest, and the percentage carbon is 4.3%. Right. So now the advantage of this is if you know the phase diagram, so you can understand. So at what temperature?
Raghavendra sir. Raghavendra sir.
Yeah.
Raghavendra sir, kindly
Yeah.
put it in full screen, sir. Full screen.
Okay. 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 So now, by seeing this, you will understand what is the melting point of a pure iron. Okay. And once I start adding the carbon, so at different carbon composition, what is the melting point and what are the different phases? Like for example, you want to do heat treatment. So heat treatment, there are different processes. So depending on the process, you want to select a temperature for a particular carbon percentage. So with the help of this phase diagram, you can identify what is the temperature you want to achieve that phase. That is the use of phase diagram. Okay, and here what is the melting point also you will understand. So this we have discussed, like ferrite is a body-centered cubic structure, austenite is FCC, face-centered cubic, cementite, orthorhombic, martensite and this thing, binite, it will not be there in the equilibrium diagram because these are actually achieved by doing fast cooling. Perlite is a mixture of ferrite and cementite. Now we have understood iron carbon diagram. Now this is one of the phase diagram of two metals. So what is your understanding by seeing this phase diagram? Anyone can tell. What is your observation? What comes to your mind by seeing this? Any answer?
Melting point is reducing in the
Okay.
mixture.
Okay. Any other answer? Any observation?
It's basically a eutectic mixture. Has got a
Okay.
low point at which the lowest melting point at one.
Yeah.
Other
Correct.
point we have
Lowest.
got two phases.
Correct. Lowest melting point we are able to see. Correct. Apart from that,
On the either side, we have got two phases, alpha and beta. Basically,
yeah,
this
that is
the
there.
phase of alpha and beta.
Correct. Any other observation?
The entire
The
system.
two
the
alloys
eutectic
can
point-
be, sorry,
Yeah, tell me, sir.
the two alloys having the same melting point and
Okay.
meeting at the same point.
Okay. So good. these are all the good observations. See, now just we'll go back to iron copper phase diagram. Okay. So here actually what we had learned is, say for example, this is the 100% iron, okay, pure iron. Here what we did, we go on adding the carbon, okay. So after 6.67, what happened is, it is not a solution. So that is why the solubility of carbon in iron is 6.67%. So that we understood. But if I see this phase diagram, here this is 100% A line is there, and here 100% B line is there. That means these two elements are can be mixed for making a solid solution at any composition. That means this element, this is 100%, you can put 100% B also, that is okay. 99% of B element, that is also can be mixed. That means it is completely soluble. So these two, that is what this phase diagram is explaining. Okay, so this is 100% B line, this is 100% A line. And other observation, whatever you have explained, that is right. But this is one of the main observation. See here, we have a lead. So this is a complete 100% lead line, and this is the tin. Okay. So with the lead line, we can able to identify what is the melting point of lead, right? So it is written over here, that is 327. Okay. And tin, you can see here, it is 232. Okay. So whatever just now we have observed, these two elements, you can make any kind of a mixture, any percentage, both are soluble. Okay. And I think for making an alloy, this thing, soldering, we need a tin and lead material. And if anybody is manufacturing this solder alloy, definitely the lowest temperature will be ideal for this application. So lowest temperature through phase diagram, we came to know that it is 183 degrees, and for achieving 183 degree melting point, so what is the composition I should have? That is 63% of tin and 37% of lead. So this we will come to know by understanding the phase diagram. Say for example, you are into this line, and one of your customer will ask, I need a solder alloy, but it should have a higher melting point for particular application. So I need say around 200 degrees centigrade. So then what we need to do?
Increase the tin.
Yeah, reduce the lead or increase the tin.
Either way, we can
Correct.
increase the tin
That
or lead.
means-
In either case,
Yeah, basically we need to, by phase diagram, we need to shift to here, say around 200, right? So that means you will know what is the percentage of lead and tin. So that is the advantage of understanding the phase diagram. See, this is actually a heat treatment process cycle. One of the heat treatment process cycle. Can anybody tell what is the heat treatment process here?
Oil quenching. Okay. Hardening.
What is the name of the process?
Hardening.
Hardening, right?
Normalization.
So now here the process is a hardening, and they have selected say 830 to 880 degree. What may be the carbon percentage?
around 0.4 or something. 0.4.
Yeah.
Be around 0.4.
Raghavendra sir, you are in mute. Raghavendra sir.
Sorry, I don't know how it has happened. Okay. Now I am audible, right?
Yes, audible. You just
Yeah.
put your
So,
PPT, sir.
yeah. It is visible, right?
Screen PowerPoint is not visible. PPT.
Now it is visible.
No, sir. Not yet.
I have shared it. Okay. What is the point?
Net is slow. So
Now it is
it's
visible,
visible.
sir.
Okay. So what we were discussing, say for example, I have a 0.4% carbon steel and I want to heat treat it. And for heating, generally for hardening and tempering, we need to first go to the austenitic temperature. So how much temperature we need to select so that with this iron carbon phase diagram, as you rightly said, 0.4%. So if you go and check here, so this area will be around 830 to 880. So generally what will happen is, say for example 0.8% carbon is there and we know that above 723, that means say 1 degree above, it is completely austenite. But during heat treatment or during any processes, what we will do is, we will ensure that around 20 to 30 degree extra, we will give that because complete transformation it has to happen. Whatever the thickness of the material is there. So for that we give another 20 to 30 degree extra so that it is completely austenite. So then we do the quenching. So that is hardening and tempering. I think anybody has got a question, I think. Hello? Okay. So this is we understood. And what is this process? Any idea?
Is stress relieving
Yeah, stress relieving. So in stress relieving,
or
any
tempering.
phase transformation happens?
No, just
Because here in iron carbon diagram, we need to understand, see this 723, this is actually a critical temperature we call it, because whatever this phases has formed, so this is not going to change once you cross 723. So if you cross 723, so then only the phase transformation will happen. Okay. So stress relieving, that is the stress relieving. Okay, there are actually three equations here. This is, we call it as a peritectic, eutectic and eutectoid. Okay. In eutectic what happens? This is completely liquid. You transform to leadovite, actually austenite plus cementite. Liquid will transform to austenite and cementite. And if you austenite and cementite, if you heat it, it will become completely liquid. So it is a reversible process. Okay. This is liquid to solid. Here it is actually both are solid only. In here austenite will transform to ferrite and pearlite, or ferrite during heating, ferrite and pearlite will transform to austenite. This is at 723 and this will happen at 1147. And peritectic reaction, this is actually at happens at 1492 degree. Okay. So these are the three horizontal lines in this iron carbon phase diagrams. So these are the three equations. What is this process? Any idea?
Is also hardening.
It is actually a case hardening process.
Yes.
Okay. So case hardening, in case hardening, what we do is we will diffuse the carbon. Okay, this is generally done for a low carbon steel, and this temperature, looking at this temperature 910 degree, so you will understand 910 degree is required to form the austenite, means the carbon percentage will be very less. Okay, so this is a 910, so this area we are hitting, that means it will be less than 0.2% carbon. So wherever you want to diffuse the carbon is not there in the steel, low carbon steel. There actually we do the case hardening process, but for doing a case hardening, first we need to convert the material into austenite inside the furnace. So how you select the temperature, that is based on the iron carbon diagram. That is why I am just asking these questions. Okay. And what is this process?
Tempering.
This is tempering process. Actually here it is a very low temperature tempering
low
process. Okay.
Stress relief.
Basically this case hardening and then hardening, normalizing, annealing, whatever the process we do, and melting. So all these processes you should know thoroughly about the phase diagram. If you know the phase diagram, whatever the temperature you are going to select, it will give you the correct results. So that is the advantage of phase diagram. Okay. I think this was the simple. I hope you have understood iron carbon diagram. If you have any questions related to iron carbon diagram, so we can discuss.
Participants, if you have any doubt related to iron carbon diagram, metallurgical, you can ask,
Yeah.
sir, so that you can clear your doubts.
Sir, any alloy additions and mixture can be called as solid solution, or is there any specific?
No, it is a solid solution only.
Mm.
Once we add any element, it is a solid solution. And actually, see, solution means if you taste any solution at any location, it will taste the same. The beauty of elements mixing in the metal sheets. So if you check the chemistry at any location, it will be same. So it is that is why you can consider it as a solid solution. Whatever the elements you are adding, you can add carbon, silicon, manganese, phosphorus, sulfur. Phosphorus, sulfur, generally it is treated as the impurities. Alloying elements, like for example, in around 10 years back, we had an issue of caster and liners that was cracking. That means during application in the engine, so it was cracking within less hours. Like in tractor, generally we give warranty in number of hours. So it was cracking within the warranty period, say for example within 500 hours. So then when we studied the reason, so we came to know that the higher temperature withstanding capacity was less. So to improve that, we added the molybdenum. So some percentage of adding molybdenum, it increases the higher temperature application. So whatever the element you are adding, like molybdenum, nickel, chrome, so it will call it as a solid solution.
Thank you.
Sir, can you explain the importance of TTT diagram, sir? Triple T diagram.
Okay. Actually, see time temperature transformation, it is also very important. Okay. So I think we can have one more session on that. So today actually, sir told me 2:30 to 3:30. Actually, I have another meeting. So definitely we will connect again. So CCT is there, TTT is there. So definitely we can discuss. And if you are interested, different heat treatment processes, that also we can connect.
Okay, sir. Any other doubts?
He's already late for his meeting.
No, actually 4 o'clock I have a meeting. So actually there are some interviews are going on. People are waiting.
Does
Yeah.
the phase diagram help us in machinability of the casting to specifically come to a conclusion? This is the percentage of carbon required, or this is the percentage of other alloys required?
See, basically, when we in metallurgy, when we call it as mechanical properties like tensile, fatigue, all those things, machinability is a critical area. Okay, so machinability depends on the microstructure, depends on the hardness, depends on the tool what you are using, speed, feed, everything. But yes, we can improve the mechanical properties by changing the properties, microstructure of the cast iron or steel. And if you have any specific problem, see basically sometimes what happens, people will say do the normalizing or do the annealing. So generally normalizing it will increase the hardness. Okay, so then it may be not useful for getting the correct hardness. It depends on the chemical composition. So generally annealing will improve, see whatever the phase structures we have seen at room temperature. See, equilibrium means very slow cooling. So annealing is a sort of a equilibrium cooling, very slow cooling we are doing. So by doing that process, definitely you can improve the machinability. But again, we need to discuss case to case. What is the hardness, what is the microstructure you are getting, and what is the issue.
Can you suggest some books wherein where we can find the all microstructure, like the Atlas of Microstructure of ASM,
Yeah,
something
Atlas of
like that?
Microstructure is there. ASTM Atlas of Microstructure is there. Actually, I don't have the copy. I will try to get it and I will share it to sir. So you can share it to all of you people. So it is there. Atlas of Microstructure is there. So there
Okay,
you
sir.
will understand the different microstructures.
Sir, there is a one question in chat box, sir. Can you check it?
Yeah, yeah. So it is not okay. I have one question. Why is the percent of carbon? See, basically, it iron can hold only the 6.67% carbon. If you go on increasing, so it is not a solid solution. Okay. Why it can hold only 6.67? Yes, I will. I need to study that. Okay. Above 6.67, it is actually a mixture. It is not a solid solution.
Any other doubts, participants?
Yes, definitely. Atlas of Microstructure. It is ASTM or ASM volume is there. I will check and definitely I will share it. Okay, so that you can share it to all participants.
Okay, sir. Any other doubts, questions?
I hope you have understood and you have learned something about phase diagram. Okay.
Sir, there is one more question in chat box, sir.
See, SG iron actually spheroidized graphite, whatever the graphite structure, no, that we are changing it to spheroidized. That is why spheroidized graphite. See, in cast iron there are different grades, right? Why the SG means basically depending on the application, we need actually the more ductile material and it should be having some hardness. That is why we go for a SG iron. So for that actually we need to change the graphite structure. So you add inoculants and change the graphitic structure. That is why it is known as spheroidized graphite. Okay. Cast iron is basically very brittle. Okay. So it cannot take the impact load. I will share my number. Okay. Sir, I think actually it was a very small topic which we discussed, and because of the time availability, and really I am very thankful for Indian Institute of IAFC, Foundry, and all the participants who have participated. Okay, so thank you very much.
Okay, sir. I think this is the time for a vote of thanks. It is my privilege to propose the vote of thanks on behalf of Institute of Indian Foundrymen, National Center for Skill Development, and the Coimbatore chapter. First and foremost, I express our sincere gratitude to our esteemed guest speaker, Mr. Raghavendra B N, founder Raghavendra Metallurgical Solution, for delivering an insightful and highly informative webinar on demystifying the iron carbon diagram, a phase transformation perspective. Your ability to explain the fundamentals of iron carbon diagrams, phase transformation, and the practical relevance to foundry and metallurgical application has made this session truly valuable for all of us. Thank you for sharing your expertise and enriching our knowledge. Our heartfelt thanks goes to Mr. Mentor Sri V. Narasimhan sir for his constant guidance, encouragement, and unwavering support in promoting technical excellence through NCSD. We sincerely thank Sri K. Dayalan, Chairman NCSD, for his visionary leadership and continuous effort in organizing quality technical learning initiatives for the Foundry fraternity. Our special appreciation goes to Sri V. Sivaprakash, Chairman, Coimbatore Chapter, and Sri A.S. Sivakumaran, Honorable Secretary, Coimbatore Chapter, for partnering with NCSD and making this collaborative take a grand success. We also extend our gratitude to all our office bearers, committee members, volunteers, and technical supporting for their planning and seamless execution of today's webinar. I sincerely thank every participants who joined us today. Your participation, thoughtful questions, and interest made this session more interactive and meaningful. We hope the knowledge gained today will be helpful in your professional journey and encourage to participate in our future technical programs. We thank everyone who contributed directly or indirectly to the success of this webinar. On behalf of the Institute of Indian Foundrymen, NCSD, and Coimbatore chapter, I once again extend our heartfelt gratitude to all. Thank you, everyone. Stay safe, keep learning, and have a wonderful day. Thank you. Thank you, sir.
Thank you.
Thank you, sir. Thank you all. Bye.